Okay, hi guys. So in this lecture, we'll be continuing on seeing more on virial coefficients, and then we'll be moving on to seeing a new concept, which is Boyle's temperature. So continuing from the previous lecture on the virial coefficients, so in low pressure range, what will happen is low pressure range, uh, and we suppose we also have higher values of molar volume. So you can neglect higher terms like just give the equation from the previous lecture that z can be written as 1 plus second virial coefficient divided by Vm plus third virial coefficient divided by Vm square, plus there would be more coefficient and would be divided by, let's say, some x upon Vm cube plus y upon Vm to the power 4 and so on. Okay, so for z equals to 1, we already know that. So before coming to this, for higher terms, you can neglect, means for higher values of Vm, you can neglect these terms, okay, because these terms already would be negligible because of higher values of Vm. So as Vm square and Vm cube come into the picture, you would get more and more lower values or negligible values, insufficient amounts. So you can directly write that for z equals to 1, you would have 1 plus b minus a upon rt divided by 1 upon Vm, or rather divided by Vm would be equals to 0. So we can write that, rather it's equal to 1. Okay, so we can write that this value would be equals to 0, and as Vm is not equal to 0, this implies that b minus art would be equals to 0. So from here we can write that b would be equals to a by rt. Okay, so from here we can write that this implies T would be equals to a upon br. So this temperature at which the ideal gas behaves, the real gas behaves as an ideal gas, this is called Boyle's temperature. So we can write Tb equals to a upon br. Okay, so this temperature would be equals to nothing but Tb. So this is very important. Okay, so we can write that real gas behaves as an ideal gas at Boyle's temperature. Okay, so next let's discuss on Boyle's temperature. Okay, so if we draw the graph of Z and P, again the compressibility factor and the pressure, so the graph would be something like this. So this is at temperature equals to Boyle's temperature. Okay, so this is let's say this was Z equals to 1. Okay, and pressure is something like here. Yeah, okay, now let's take some more examples. So suppose we have this graph in which we have again the graph between Z and P. So we would have the same hydrogen gas at T1 equals to 0 degree Celsius. Okay, and the same hydrogen graph at T1, or let's say this is at T2. Okay, and we are not defining any range for T2, but we know that for hydrogen gas TB is equals to 110 Kelvin. Okay, so T1 is greater than obviously TB, and for this graph you have to tell whether what is the nature of T2. You have been given in the question that for the hydrogen gas at T1 equals 0 degree Celsius, the nature of the graph is this, and for T2 temperature we don't know the exact value. The nature of the graph is like this. Okay, and we know that TB for hydrogen gas is 110 Kelvin. Okay, so T1 was greater than TB because T1 was 273 Kelvin, hence the nature of graph was this. So what would be the nature of T2? T2 would be less than TB. Why? Because it is going down the z equals to 1 line and then coming up. This implies that this will not behave as an ideal gas for the pressure range of between this to this, and had it been behaved as an ideal gas, or whether T2 was, whenever T2 was equals to TB, then compressibility factor would be something like this. The graph would be something like this, as the compressibility factor for temperature at TB for hydrogen gas would behave as a ideal gas. Okay, so similarly we can draw the graph for nitrogen as well. So suppose for nitrogen we have this graph between Z and P, this is equals to 1. So suppose we have this graph for nitrogen at, let's say, temperature T1. So we know that for nitrogen Boyle's temperature is let's say 54 degrees Celsius. Oops, 54 degrees Celsius. So for T1, this T1 would be greater than TB because it is going up the z equals to 1 line. And for T2 temperature, let's say T2 temperature here was given 0 degrees Celsius. So as T2 is less than TB at 0 degrees Celsius, then the graph of nitrogen would go first below the line and then above the line which is z equals to 1. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing more on the liquefaction of real gas. Okay, so till then, good luck and goodbye.